it in. So let's get recording, shall we? Last week we looked at, at magnetism, and we looked at it in a quite complex way. You had quite complex things to do with magnetism, but not so much this time. I'm going to show you some kind of complicated ideas, but we're just really going to talk about it. So last week we looked at magnets. You have a north and south pole. The law of magnetism, like poles repel. So north and north, south and south repel. Unlike poles or opposite poles, I got hiccups, attract. The space around a magnet that you can't see, that influences or pulls material towards it, it's called a magnetic field. They go from north to south. My little cool diagram. I spent years doing that. There you go, north and south pole. My lines go from north to south. Magnetic materials, iron, steel, nickel, cobalt. All right. When you have induced magnets. Oh, what a lovely cup of tea. Right. Some materials and become magnetic when they're near or touched by a magnet. And a really cool one is a paper clip. And if you put a paper clip near a piece of iron, like an old iron nail, it'll do nothing. Put the paper clip on a magnet, the paper clip becomes magnetic. Only if it's near that magnet, or if it's in a magnetic field. And that's called induced. Induced means it's made it magnetic. All right, now electromagnets is what we're really looking at today. And we're looking at the language of electromagnets. Now, you take any wire you want, any wire, right? You attach it to a battery. You let, look at the state of that battery symbol. You let electricity flow through it. You let current flow through it. It creates a magnetic field around it. Now, how do I make this stronger? Well, one of the ways of making this stronger is to take that wire and coil it, right? There's still a wire. I've just changed it into a coil. So instead of saying, dude, I've just changed this wire into a coil, being science, we give it a really crazy name. And we call it a solenoid. All right? And by putting coils in your wire, you make that magnetic field stronger. See, how in a strong magnetic field? There's no point playing with magnetic fields if you can't make them stronger and maybe do a magneto. So anywho, how else can I make it stronger? Another way is by giving it an iron core. So wrapping those wires around a piece of iron. That makes it even stronger. How can I make it even stronger? Well, use more coils. Well, if I want to make it even stronger than that, well, increase the current going through. So let's stack some batteries in there, right? Increase the current, and there you go. All right. Now, we have something more interesting as well. It's called the motor effect. So I'm going to talk you through. What do you want?
Some paper.
All right, get some paper. Yeah, I can just kick my charger out, you cheeky girl. All right, so the motor effect is even cooler than. Oh, do you know what? Let's go back to electromagnet. So one of the things I love about electromagnets is scrap card electromagnet. And I'm going for an image. And there you go. And this is how we use electromagnets. I had an image of it somewhere. All right. So this is how we use electromagnets. All right. Let's zoom in. So there's lots of wire in here. And you can see this pass of power cable going in. And there's wire going around and back. And there's a chunk of iron in there. Turn it on and off. You can turn that in your magnetic field on and off just by turning the current on and off. So the motor effect, now that's really interesting. If I've got a wire and I attach it to a battery, well, you get this magnetic field around it. If I put that wire inside a magnet, and this is North Pole and South Pole, and I've got magnetic fields going across there, this wire will jump up. It will experience a force. That's it. That is the motor effect. That's how electric motors work. And Fleming, and I keep wanting to say Ian Fleming, it's not Ian Fleming because he wrote James Bond. Now, Fleming came out with Fleming's left-hand rule. Something you're not going to use for a couple of years. But I'm just going to start, as I said, and introduce you to stuff. This is direction of the magnetic field. So your knuckle sits on north. That's where my magnetic field is. My current, this is the second thing that tells me where my current is. In this case, my current is going that way. On my diagram, my magnetic field is that way. So the wire is going to move in the direction of my thumb straight down. That's Fleming's left-hand rule. All right. Okay. Now, the equation is a really cool equation, F equals Bill. And we're not going to use them that much, but we're going to use them properly. And this one we're not going to use today. We might use it next time. Hold on, cup of tea. Back to my cup of tea. And I just want to talk about it because units are important and just getting used to them. F equals force. So the force by which this wire is going to move, and force is always in newtons, right? After Sir Isaac Newton's, equals B, magnetic field strength. Units are Teslas, named after Nikola Tesla, not Elon Musk's car. Times I, which I hope you remember from last year, is current, and L, the length of my wire inside the magnetic field. All right, but just the length of my wire. The generator effect is the opposite. So instead of having your wire here, attached to a battery, you don't. And if you push the wire, you generate electricity, and that's called a generator effect. All right, and you find it in wind turbines and everything. All right, and here we've got applications. Usual. How do you make the motor effect or the generator effect bigger? Use a bigger magnet. If you're generating electricity, move your coil faster, or use more turns of wire. All right, so what applications have we got? Scrapyards I showed you, door locks, MRI scanners, electric motors, loudspeakers, dynamos, microphones, transformers, which we've looked at. Your first task, oopsie day. Why? Oh no, the answers, I better hide them. That's a bar magnet, get rid of it. As much as that's a bar magnet, these are opposite poles. They're attracting each other. So you've got to look at attraction, repulsion when the poles are the same. This is a compass. And a compass reacts or points to the magnetic north or south, whichever one does both. Here is the magnetic field. This is iron filings being pulled out of sand using a magnet. X and Y, X and X is poles, those are magnetic poles. This is called a horseshoe magnet. That's an electromagnet in a scrapyard. And more magnetic fields. Oh, they're magnetic field lines. Oh my God. So this is the whole magnetic field, and those are magnetic field lines. Solenoid with an iron core. This is the motor effect, and this is Fleming's left-hand rule. I've gone fast through that because I do record these. 10 easy questions, 10 medium questions. And that's all I'm going to leave it at that. Because